availability, maintainability, and safety software products. We have offices in the UK as well as in the US, and we're a very mature software. And when I say that, we're deployed in over 10,000 sites worldwide, and in many large organizations utilize our software. And just to kind of jump in here, let me switch over. Sorry about that. All right, the team that we have on the line here today, we've got myself, Brett Peterson, North American Sales Manager. We've got Joe Belland. He's our lead technical support, been with the company over 15 years. Those of you that have had the opportunity to work with Joe, you'll know he's got a ton of knowledge. He's very helpful, and he's worked with a number of industries across the board. So it gives everyone a great insight when you have a question, something comes up. Joe's going to be doing the bulk of the presentation today and answering questions that come up. I've also got Jeremy Henoch on the line, Director of Operations, and Jeremy's been with us over 18 years. So got a great team here to support you and make sure that we have a good use of your time here. Cool topics that we're going to touch on today that Joe will be going into is really how to justify your maintenance strategy and cost. You know, when maybe you have to report to a manager or upper management and go through those things, we'll show you how the software can help you do that, coupled with optimizing spare parts holdings, and when you might want to consider replacing, refurbishing, or repairing, and identifying really that cost benefits ratio. So we'll be hitting on some of those topics today also. Now, one place that you'll find a lot of resources from Isograph, we host most of these recorded webinars on our blog. So if you haven't had a chance to visit our blog, jot this down. And there's a lot of content, resources, and tools there for you to do some additional training. One housekeeping item before we jump in. Those of you that aren't familiar with GoToWebinar, in the bottom right-hand corner, that box that says questions, if you wouldn't mind, if you have a question that comes up, post it right there. Due to the fact we have a pretty large group on today, just post your questions. Joe periodically will pause, ask questions along the way. And if it's something that's, you know, relevant to the overall group, I'll make sure to pose that question to Joe and we'll get it answered. If it's not, and it's more kind of a one-off, still feel free to post it there. It'll just come to me, and I'll make sure to jot those down and get back with you after the webinar and get answers to your questions. I really appreciate that. Now, as many of you know, there's a number of modules found within the Availability Workbench. The two that we'll be touching on briefly will be AVSIM and RCM cost. And one quote I love that most of you have probably seen multiple times, but the only thing worse than training your employees and having them leave is not training them and having them stay. So I commend each of you for being on here, enhancing, you know, your skill set, as well as, you know, I know that ends up converting to the bottom line for your organizations of improvement and continual training. So wanted to thank each of you for being on with us today. Feel free to jot down any information here also. Any questions that come up maybe after the webinar, you need any additional information from myself, Joe, or Jeremy, feel free to shoot me an email or give me a call, and be happy to, you know, help out however we can. With that being said, let me transfer the screen on over to Joe here, and we'll dive on in. All right. You should have that here in just one moment, Joe.
Okay.
Perfect.
Thank you, Brett. I've shared my screen, so hopefully it should load for most of you in just a second or two. Okay, thanks for the introduction, Brett. I like that quote. Ideally, you'd like to train your employees and have them stay. So that's what I'm here for, to train you and train you up a little bit more. I know of probably a few of you, just looking through the attendees, I know a few of you already have some experience with the Availability Workbench. So hopefully I'll be able to supplement that, maybe teach you a trick or two that you might not have already known. As Brett mentioned, we're going to be going through the Availability Workbench, specifically the AVSIM and RCM cost modules. For this one, to make it a little bit interesting and differentiate it from past webinars we've done on the Availability Workbench, I'm going to be this is actually going to be building a model from a schematic. We once did that in the past with our, or we've done it a couple times in the past with our Reliability Workbench and our fault tree software. So I thought we'd have a little bit of a change and do it for the Availability Workbench software, starting with the schematic. And since the Availability Workbench is a much more complicated tool than the Reliability Workbench and the fault tree, there's a lot more sophistication and complexity you can put into the models. That's just inherent to Monte Carlo simulation. I've decided to keep the model a little bit easier, a little bit simpler than what we normally see. So I have a schematic, just a very simple schematic for a system, and it looks very straightforward, but there's actually some rules about this system that make it turn into an interesting and somewhat creative case study. This model that I'll be building is, I'll say it's inspired by actual events. You know, sometimes you go to see a movie and they say it's based on a true story, or there's a descending order of truthfulness. Based on the true story is the highest, and inspired by actual events is sort of the lowest order of truthfulness. And I'll put this at the lowest one, inspired by actual events. It's sort of based on a model that was once shared with, that I once worked with a client on building. It's been changed heavily since then, but it is based on something that an actual modeling problem that someone did once come to me with. And so I thought it would be an interesting case study that we could go through. So anyway, the schematic, as you can see, is actually very simple. This was what they were modeling is a pumping station. This was along, I think, a natural gas pipeline. You had your wellhead, or your well was in one location, and then they had several miles, like 50 or 100 miles of natural gas pipeline leading to the to the refinery. And so they pumped it from the well to the refinery. And along the way, there were pumping stations to keep the flow going, keep the flow of the natural gas going. And they wanted to model those pumping stations, the availability, the capacity modeling, and the throughput, and also just of those the pumping system, moving the natural gas from the well to the refinery. They did have some interesting facets to the system. Firstly, the pumps themselves were not necessary for the operation of the pump system. The pumps increased the flow, they added to it, but if the pumps were offline, there was sort of just a natural flow. The natural gas would just naturally flow downstream. So the pumps increased that flow, they sped it up so they could get more gas and therefore more processing and more refining, and of course make more money. But strictly speaking, they didn't need them to get some availability. So along the way between the well and the refinery, they had two pumping stations. Each pumping station consisted of the pumping equipment itself. Here I've represented it with one pump, and for the purposes of the example, we'll keep it simple and easy that way, with just one block to consider. But in reality, it was actually represented a group of equipment. There's various valves and pumping apparatus, and control mechanisms, and things like that for each pump station. For its simplicity's sake, again, we're keeping it simple. So each pump station consisted of the pump itself and also a check valve. Now, if the pump was not operational, they would just divert the flow through the check valve, and you'd still have flow, but it would be a little bit reduced. If the check valve failed, at the same, conversely, if the check valve failed, like it failed close or something like that, so long as the pump was still working, the pump station was still considered fully operational. So you could take the check valve offline, do maintenance on it, it could have a failure, and so long as the pump was working, you still had flow through that. However, if both pump and check valve were failed, then that pump station would be completely offline. It would completely block the flow. So that was something they wanted to avoid. They wanted to keep at least some equipment in the pump station online. So now here's where the interesting capacity model comes in this example. is that each pump station can contribute about 25% of the total flow of the system. So if you have both pumps online, you're at 100% or maximum capacity. If one of your pumps fails, so long as its corresponding check valve is open, you drop to 75%. You drop to 75% capacity. You lose, that pump adds about 25%. If both pumps fail, just going through the check valves themselves with no boosting stations along the way, with no boosting, you're at about 50% of the maximum capacity. So you still get about half of your maximum production. So that's good, but not great. Of course, we always want to strive to maintain maximum capacity and throughput for the purposes of, well, this was mainly financial considerations in this particular model. This was more of a throughput rather than a safety model that we're building. Okay, so that was the interesting capacity requirement, and it actually made constructing the model to simulate this system. It presented some interesting challenges that we had to overcome. So let's go through that. Let's actually use the availability workbench and start in the AvSim module to simulate this system complete with its sort of strange capacity and availability requirements. Okay, so I have the availability workbench open to the AvSim module, new blank project. So let's begin from there. We'll start by, when I did my building a fault tree from a schematic, I did the same thing. We'll start by adding the schematic onto the diagram so I can see what it is that I'm building as I construct the model. Okay, so I'm going to start by creating a new system, my new RBD page, and then I'm going to add a bitmap to my project, so add a bitmap. This will represent the pumping system. And I'm going to browse for my bitmap file. Well, it says bitmap, but really any project file will work. So presentations directory. I always mess things really too far deep. Anyway, it says a bitmap, but I can look for all files, and I have a PNG file of that pumping station. So let me open that and attach it to the project. To display it on the system, in the system background, I can put it on a label. So let me add a new label to the background. Added a label. And then I just simply drag and drop that bitmap onto the label. It's a little small, so let me resize it, make it a little easier to read. There we go. So that's the system we're going to be modeling. So we can use that as a reference as we build this. So let's build it sort of straightforward. Right on that schematic. So we have two pumping stations. Each pumping station consists of a pump and a valve in parallel. So let's build it that way. Again, it's pretty straightforward. I'll add a node at the beginning, intermediate node, and the node at the end. And then we'll add blocks for the pump and the valve for each pump station. To be able to edit and then lastly I need connections. Drawing connections to connect everything up. Okay, there we go. And of course, you can rearrange the diagram. If you're like me, I'm a little bit perfectionist on everything has to be arranged nicely. You can click and drag to move things around. Or again, remember, you can always use the keyboard shortcuts, Control L, R, U, and D, to sort of shift things around incrementally. So if I select the node and use, of course, you can't see my keyboard, but I'm using Control D to move it down, Control R to move it right. I can sort of shift things around, Control up to make that. And it looks a little bit nicer when you shift things around as such. And again, Control L to move that to the left. Okay, so that looks a little bit better. So we've got our diagram. We want to label everything, obviously. So I can go to the diagram in grid mode. I've been, if you've been to my training sessions or you've had previous webinars, you might have heard me extolling the virtues of the diagram in grid mode. It allows you to get a table view of your data. So let me see the blocks table. So there's a list of all the blocks in my project, right? And this gives me a table view, and it's much easier to edit rather than double-clicking on the blocks and typing in text there. I can just type the text in the grid view. It's a lot like using an Excel spreadsheet or a Microsoft Access table. So this is pumping station, the first pumping station pump. So pump 1 is block 1.1. And then block 1.2 is actually the check valve. So I'll put CV1. And similarly for the other two, pump 2 and the CV2. Okay, so I can add IDs, and also I might add descriptions if I want to, if I so choose. This particular example, I don't need to. You know what these represent. Okay. One last thing is now we've got the availability model. This captures the availability of the system. If one of the components fails on that line, or in order for the system to be unavailable, you have to have complete blockage in one of the pumping stations. So both the pump and the check valve in a pump station have to fail. Now but the problem with this construction of the model is that it's very difficult to do the capacity model. So remember, the capacity is that when the pump fails at a pump station, our overall capacity drops by 25%. Now we could probably do that. Let me go to the view options and turn on to show the capacities underneath the blocks. Okay, so they're all set at 100%. What we want is that when this fails, the system throughput should drop to 75%. So maybe we could set the check valve to 75%. Okay, so where's my maximum capacity? That at 75%. You can do that for the other check valve. So now we're capturing the scenario that if pump 1 fails, now the system's capacity is at 75%. That's the remaining for the check valve. But what this is not capturing is that if both both pumps fail, system capacity should drop to 50%, right? Because the pumps have a sort of a redundancy to each other in terms of capacity, not in terms of availability, but in terms of capacity. And this model isn't really capturing that we lose both pumps and we drop to 50%. So that gets a little trickier to model. So we can have another iteration of this. So let's talk about how we do the second iteration of this model. So as I mentioned, the pumps have a redundancy to each other from a capacity standpoint. So what I'm going to do is I'm going to put those two pumps in parallel for capacity. And I'm going to do that by creating copies of them. I select the block, hit copy, and then I right-click on the background and hit paste. Not paste special, by the way. If you're an expert user, you know the difference between paste and paste special. It's supposed to represent the same pump. I want them to be linked. So if it's failed, right? I'm not simulating a second or a third pump here. This is the same pump 1. I'm just using it a different way to construct a different model. I'm going to do the same thing for pump 2 and copy that, paste it as well. Okay, now they're redundant to each other from a capacity standpoint. So I'm going to create a second capacity model. Okay, so this is interesting. Now I have these pump 1 and pump 2 are in series with each other. Now that's why I've duplicated them. Now at this point I'm sort of going a little off book. This model, this RBD model, doesn't represent the actual physical layout of the components. Instead, what we're trying to do is capture their logical behavior. So my my block diagram doesn't look like the way the system is physically connected, but what I'm building is the logical model. Okay, so now this since they are redundant to each other from a capacity standpoint, each pump, if I lose a pump, my capacity drops 25%. So let's put each one as 25. Now, of course, this still here doesn't quite capture it because for a parallel arrangement like this, the capacity through the arrangement is the sum of all the blocks in parallel. So this makes it look like the maximum possible is 50% because that's the maximum I can get through the system. So that doesn't really work either because I should get 100% when they're both online. So how do we do that? This is where we start to get really tricky and really clever and sort of start to game the system, so to speak. What I'm going to do is I'm going to create a dummy block. Now, a dummy block is a block that represents, or that's used in the model to force a behavior, but represents no actual physical components in the system. So a dummy block, it's not any real thing that exists. Rather, it's something that forces a particular behavior. So I'm going to add a new block. And usually a dummy block will have no failure model attached to it, or in some cases it might, but that's only to trigger a specific behavior. It doesn't represent an actual physical component failure or failure mode. So I'm going to call that my dummy block. Dummy for capacity. How am I going to use this? I'm going to put it in parallel with the other two pumps. And then I'm going to assign it a capacity, 50%. Okay, so presto, these three blocks together sum to 100%. So long as both pumps are working, I have 100% throughput. One pump fails, I drop 2, you sum the remaining 2, it's 75%. Both pumps fail, I'm at 50%. So I've now accurately captured the capacity model of my system. So long as they're both operating, we're at 100%, both failed, 50%, etc. That's an accurate model of the capacity model. The problem here is my availability model, because I still need my check valves, I still need the pumps and the check valves in parallel with each other for the availability model, right? If both the pump and the check valve fail in one pumping station. The problem here is that this availability model is interfering with the capacity model. If I lose this check valve, my throughput through the remaining pump drops to 25%. But that's not how the system behaves in real life. If I lose my check valve, the systems can still operate at 100%, so long as the flow continues through both operational pumps. You can lose the check valves and they can be offline and still have 100% capacity. So my availability model is interfering with my capacity model. Okay, so so how do we do that? Now this is where it got really tricky. This is when the customer I was working with presented this problem to me. I actually had to sit and think about it for a day or two. I drew it out on the whiteboard in my office and put my brain to it. What we finally came up with when we put it all together, it was, again, a really tricky way of doing it. So what we want is that we don't want the failure of the check valve to influence capacity. We do want it to influence availability. So again, I'm going to do a little bit of a rearrange of my system. Let me show how I'll do this. So let's see, delete that node, rearrange my pump systems. I'm going to move this one down here. In essence, putting it in parallel. Move that one down, move this one up. Again, a lot of this is just sort of fine-tuning. Okay, so I'm sort of getting there. There's a little bit more I need to do. Let's see if you can identify what I'm doing here. Putting them in parallel. Now I'm going to be a little creative about it. They look like they're in parallel, and that works for capacity. Then I'm going to put a vote number on this final terminating node here. I'm going to set the vote number to 2. That means at least 2 of these connections to it must be active and available. That means if one of these pumping stations fails, then we no longer meet our availability requirements, the vote requirements, so the system is considered unavailable. Not meeting that vote requirement 2 if one of these pumping stations fails. However, for the purposes of calculating capacity, it sums all the available paths. So if a check valve here fails, then actually I can put the check valves back up to 100%. So if a check valve here fails, it's going to do 25% through here and then 100% through down here, so we're still at 100% capacity. So the check valves no longer influence the capacity, except in one case. There is one case that's sort of breaking it. So that's if both check valves fail. We're only going to get 50%, and that's not what we want. So again, how do we get around that? Well, guess what? With another dummy block. We create another dummy block on this system down here and put that in parallel with this whole system. This dummy block will have, see what I did actually, using the extra node as an extra control point. So I get my connections to look nice. There we go. That's a little bit better. This is dummy 2. Okay. And then I'm going to adjust this vote here to 3. Okay. So now I have captured the availability with this. If I lose a single pumping station, I'm no longer meeting my vote of 3. However, these are incapable of affecting capacity. So long as the vote number is met, I guaranteed have 100% capacity through my dummy block down here. This prevents this arrangement from ever influencing capacity. So I've captured both the capacity model with this arrangement here and the availability model with this arrangement here. Okay, makes sense? Okay, Brett, I guess now would be a good time to pause for questions. I probably should have started a bit earlier, but yeah, if you've got any questions that you want me to address at the time.
Yeah, one question that's kind of, I guess, a broader question is that was asked is what are some of the key differences between if you would go with like the RCM cost module versus the AVSIM module? When would you select which module?
We'll actually get into the RCM cost. That's actually going to be the next thing that we'll get into, is showing the RCM cost and what it contributes to the tool. So the AVSIM, I started here in the AVSIM, this is a complex requirements. It's an overall system look. RCM cost is more of a targeted, focused, looking at assets one by one to optimize their maintenance. And that's actually going to be the next thing we're going to be doing. That's a good segue to move into the RCM cost. But before we do that, I'll answer any other questions.
Perfect. One other question was, from this stage, what are the reporting capabilities, or if they need to put it in a format that they need to go present it to management or to other team members?
Let's save that to the end. I'll go through the reports that we'll get from this model. At the very end, we'll show the different graphs and system reports that we can produce that show our requirements. Okay, but I'll save that one. I'll answer that one at the end of the.
Perfect.
Okay, so let's fill this out. I've captured the logic model of the system, but there's obviously a few pieces of data missing, and I'm not going to go into them in too much detail. This is more, I think, you can refer back to some of the previous webinars or how to do this, or our training. Our full training will cover how to add the rest of the information. So I'll just mention the other information that I need to add. I need to add failure models, the failure data, how often each block fails. I need to add maintenance data, what's the corrective actions and preventative actions that we can do, preventative maintenance actions we can do. And the RCM cost will help us optimize those and do that in a little bit. I'll want to define consequences. What happens when a failure occurs? How much does it cost? Or what's the risk to safety, operational, or the environment? And lastly, spare parts. Those are the three other things that I'm going to consider in this model. Now, I'm not going to go through, just for the sake of time, for this particular webinar, I didn't want to focus on where you put in each one of those pieces of data. I didn't want to go into that in great detail. So I'll just show you the completed model once I've added that. Here, just give me a second to open up the completed model. I have it on another. Okay, on another screen, and another instance of availability workbench. Okay, so this is basically the same thing. It looks a little bit different. I built this one separately previously to it. So again, just the same pump assemblies, check valves, the two dummy blocks, dummy bypass for capacity, dummy bypass to prevent this from influencing capacity. Put a few labels on this one to identify why I have those two systems, because someone looking at this would not understand why I have the same pump in series with itself. That doesn't really make sense. So it explains a little bit more what I'm doing here. Okay, the other thing is I've added to this model, when I've added failure models for the pumps and the check valves. I added failure data, so the pump has a bi-Weibull distribution to define its failures. It has some maintenance. I've said when it fails, what's our maintenance task? It takes us 8 hours to replace the pump. It takes a spare part. We have the pump spare part that I've modeled. I also have a planned maintenance. I'm going to look at the planned maintenance in more detail in the RCM module. I'm going to examine those planned maintenance tasks. I've added a consequence. The consequence got added to the overall system. The consequence has to do with the cost. How much does it cost if we lose capacity? So I've said that there's a target production level of 75%. So I'm trying to maintain at least 75%. If we lose percentage, so long as we maintain at least 75% production, it costs us $100 per unit lost capacity per, I think it's per hour of my time units in this project. So $100 per hour per unit of lost capacity, so long as we're above our target. If we drop below our target, now it becomes more expensive. Presumably there's requirements or contractual obligations that they maintain a certain throughput. So if we drop below that production target, then our cost jumps up to $1,000 per hour per unit. Okay. So I've added those consequences. Lastly, the spare parts. I mentioned that we've added spare parts. So let's just take a look at the spare part. I've said that I've defined a pump that costs $10,000. This is required to do the maintenance on any of the pump assemblies. And we're going to look at this pump storage, the spare part storage, and optimizing that spare storage. Once we move into the RCM cost module, we'll take a look at optimizing this. How many pumps should we keep on hand? Okay. So let's run the simulation. Actually, let me make sure. I think I set up my settings. So 10-year lifetime, 10 profile intervals, 100 simulations. Well, let's set the capacity availability as well, just so we can see that. Okay, I think that's all I should need to do. I can run the analysis, and let's just get a look at the results. So the simulation results tell me the total costs, the breaking down between spare purchase and the consequence cost. That's the main cause. It's when it fails and we're losing capacity. That's the main cost of the system. We can also look at the system, the downtime, the mean capacity, the mean unavailability, various other performance measures. And again, if you've used apps and you're familiar with it, you're probably familiar with all these outputs from it. Okay. So let's just take a look at one of the plots, or a couple of the plots maybe, that we want to look at. So there's the cost profile, but what I was after was actually I wanted to see the system profile. Let me modify this to show the capacity. Turn off my error bars. Capacity over time. Okay, so if you'll notice, it looks like it's big jumps, but if you notice the Y scale, we're only looking between 98.4% and 98.95%. So it's sort of jumping around. That's probably as things are wearing out, because it's sort of a predictable wear out to the pumps and the valves. And these jumps are really not that big. They're within 0.2% for most of these waves. Anyways, we can get a plot of the system profile, the capacity profile, and also of this is another one that might be useful. A user just the other day asked me how to get this plot, the capacity availability plot. This plot shows you the probability of meeting or exceeding a given capacity. Okay, so it's a little bit hard to read because it's going from 0 to 100% availability. But we can sort of focus in on this if we set the plot options. Actually, if I set it automatic, no, I want to actually set the minimum. So this is around, let's go between 0.9 and 1. Okay, so how do we read this? This is the percentage chance of meeting or exceeding a given capacity. So if we want to know what's the probability that we're going to meet our 75% production target, well, that's 75% right here, right there. So the availability for meeting 75% capacity is about 94. Yeah, there it is. Let me find the tooltip. There it is. About 0.9993. Yeah, 0.9448. There it is for 75%. I don't have a data point at exactly 75%. So we'll use the next highest one. 94.48% chance of meeting or exceeding 75% capacity. So that's how we can use the capacity availability plot. Okay, so that's a couple of the reports. Or a couple of the outputs. I'll go into these in more detail in the reports later, but I'll just mention you can directly print these. Or you can create a clipboard image and paste it in, say, Microsoft Word or into some other documents so that you can print up and give to management. Okay, so that's sort of a preliminary analysis of our system. But one of the things that that we want to do on the system is optimize. Right? When should we be performing maintenance on the pumps or the check valves to minimize the downtime and maximize throughput, or minimize cost, really, is what we're after in this model. So the RCM cost, I mean, AvSim does have a the interval optimization feature. But RCM cost has it sort of more robust. It's a little bit more focused on that. So I want to build this in RCM cost. So how are we going to do that? Well, we could just recreate the model in RCM cost, or there's actually a simpler way. We go to the tools, and then the convert, and then RBD to locations. The locations hierarchy is what we call the RCM cost, the FMEA, the failure modes effects analysis hierarchy. It's called the locations hierarchy. So convert RBD to locations will take all the data here in AvSim and essentially create an RCM cost model out of the AvSim model. And what's more, when I do that, now you'll see an RCM cost created that. It created each one of those blocks. Let me expand these all. So I created my 2 pumps, my 2 valves, and it even copied the dummy blocks, but I don't really need those. Those don't represent anything real. I don't need to optimize them. So I'll delete the 2 dummy blocks. Okay, so it created those pumps and valves in RCM cost. But what's more, it also created data links. It data linked the absolute failure model to the RCM cost cause. What that means is when I make changes to one or the other, it's very easy to propagate those changes back. So if I use RCM cost, for instance, to optimize my planned maintenance, I can very, very easily copy that back into AvSim. You can copy those changes, those optimized maintenance intervals, back into AvSim. So let's do that. Let's actually take a look at that. So right now the pump failure model is linked to pump 2. So since there are 2 causes, there are 2 pumps, and they were using the same failure model in AvSim, one cause can only be data linked to one failure model in AvSim, so it chose the second one. So essentially these 2 pumps are identical, right? So we only really need to do our asset management or our asset optimization on a single one of them, right? Because they're both basically the same. They're going to have the same maintenance intervals and maintenance policies. So I'm going to pick the second one, collapse that first one, and we're going to optimize this. Again, it has all the same information. One thing it did not copy is the consequence. So I'm probably going to want to set up an effect in RCM cost. What's the effect of failure? It cost the failure of the pump. We dropped 25% capacity, which I said was going to be about $100 per hour per unit capacity, so multiply that by 25. So we'll say it's $2,500 per hour to lose one pump on average. Okay. Actually, we should call it loss of capacity or something. Small loss of capacity. Okay, so I'll assign an effect, and that way we can track the costs of the outage and the costs of the maintenance. I'm going to say that effect only applies to failures. In other words, we can plan the maintenance on the pump so that it doesn't affect our throughput. Maybe we do it during scheduled outages, or we can schedule downtime for the planned maintenance. Okay. So I have an effect. I have my same failure data that came from AvSim. I have my maintenance tasks that came from AvSim. So let's take a look at that planned task. We were going to optimize this maintenance interval. It's going to help us figure out what that should be. The task takes 8 hours, and it takes a spare part as well. We have to replace the pump. There's a planned replacement of the pump. We're going to ask how often should we do that to minimize the costs of the system. Okay, so to do that, I'll go to the Strategy tab. And to get an idea of what we expect to spend on a single pump over the lifetime, I'll just run the simulations on just this one asset. So I have an overall cost. This is mainly the cost due to outages of that one pump. I have a failure downtime, a mean unavailability, outage frequency, number of lifetime failures. And actually I realized this cost isn't really accurate because I only added one effect. There's a 100% chance of a small loss of capacity. There's also a chance of an additional loss of capacity, and there's also chances of a total outage, right, depending on if the other check valve fails. So we might want to add an additional effect. If the check valve fails, we're going to have a total outage, right? And that's much more expensive to cost rate for that would be, 1,000 times 75, so 75,000 plus 2,500. So 77,500 would be the cost per hour for a total outage. But that doesn't guarantee it happen with pump failure. That only happens if the check valve fails as well. So I'll put a redundancy factor. How often is the check valve out of service? I'll say about 1% of the time, I'll say. Okay, so now with that, I forgot that effect. So let's rerun it and find the new costs of it. We got a new cost associated with this pump. Now let's optimize that planned maintenance. How often should we be doing planned maintenance to minimize the cost? So I'll go to the interval optimization. And the way the interval optimization works is it's going to try, let's say 30 different maintenance intervals. Each maintenance interval will be 730 hours longer than the last maintenance interval that it tries. In other words, what it's going to do is it's going to set in a maintenance interval of 730 hours. So in other words, what would happen if we did maintenance every month, monthly maintenance? Runs the simulations, records the cost results, right? And then it increments that maintenance interval by 730 hours. What happens if we did maintenance every 2 months? Run the simulations, record the results. What happens if we did it every 3 months, every 4 months, every 5 months, etc.? It's going to do that for 30 different possible maintenance intervals. In other words, it's going to be considering maintenance from intervals of 1 month to intervals of 30 months. It's going to run the full simulations each time and record the results and report back which maintenance interval had the lowest overall cost. So let's do that. I'll quickly start optimization. Took it a second. So now you can see on the left-hand side of the graph, this is the short maintenance intervals, right? The x-axis, the independent variable, is the maintenance interval. The y-axis is the cost of performing that maintenance, right? So the left-hand side is very short maintenance intervals. We have a higher cost due to overperforming the maintenance. We're spending a lot on spare parts, on those. We're buying a lot of pumps that we really don't need. It's $10,000 per pump. We're buying more than we need, so we're wasting money on doing unnecessary maintenance. On the right-hand side, we have a very high cost due to unplanned outages. We're having the pump fail, which can cause unplanned outages, which again is leading to a very high cost. So the low point, it says, is a PM at 8760 hours, yearly PM. If we replace the pump after 1 year, that's when we meet our lowest overall cost. So if I like that, if I agree with that recommendation, I can click the accept recommendation, recommended PM at 1 year. It sets the maintenance interval. It checks the planned maintenance, and now I can rerun my simulations. I'll get a new cost, new downtimes, new PM downtimes, etc. And I'll get a cost-benefit ratio. The cost-benefit ratio tells us the cost of running with a run-to-failure maintenance, or excuse me, the cost of running with this maintenance policy divided by the cost of running with a run-to-failure maintenance policy. So this only costs just under 80% as much if we do this maintenance versus if we did not do this maintenance. In other words, we will save about 20% of what we would otherwise spend if we did not do this planned maintenance. So this is generally the number that management would want, is how much are we going to save by doing that maintenance? What's it going to give us? And so that cost-benefit ratio is the number we're looking for. Okay. Before I stop and ask questions, one more thing is now that I've optimized this, how do I get it back to the Avsim model? Click OK. I'll go to the data links, edit data links, and you'll notice this little symbol here indicates the data discrepancy. What that means is the data in the Avsim model, the Avsim failure model, is different from the data in the RCM cost cause. So that's what that means for the pump. So now I can update it. I can update data left to right, copy the Avsim data into RCM cost, or I can update data right to left, copy the RCM cost data into Avsim. That's the one I want, update data right to left. Select that, and now it will have updated. If I go back to Avsim, open that pump failure model, look at the maintenance tab, it will have updated the maintenance interval and have checked the task enabled. It will have set the maintenance as we've optimized it in RCM cost. Okay, and I think that's my breaking point to ask for more questions. Brent, is there any questions you'd like me to go over?
Yeah, one question is, kind of, what is the communication capability with regards to bringing data in, out from like ERP or SAP or that type of stuff? How does that?
Yeah, that's a perfect question. We have a lot of capabilities for bringing in external data. So I'll just run down a few of them. Obviously, we have the import and export wizard, right? These imports and export wizards allow you to import from, say, an Excel spreadsheet, an Access database, a text file. But really what most people are after is, again, as I mentioned, the portals. If I go to the module selector, we have SAP and Maximo connections. Also from the ERP portal, I'll connect to Ellipse, Mincom's Ellipse system as well. And these link to the RCM cost module specifically. I have maybe at the end I can show it. I have an example file that shows you the types of data. But you can essentially download data directly from SAP or Maximo or Ellipse into the RCM cost module. So the data that you'd get would be essentially that cause, or that the failure mode hierarchy that we saw in the RCM cost module. It downloads the work order or the maintenance plans from SAP. It downloads your assets. It downloads your basically all the information that's relevant to RCM cost. You can download work order histories for the purposes of calculating a failure rate. And then you can optimize, and you can even put data if your administrators let you. A lot of people, their administrators don't like, their SAP administrators don't like other programs directly dumping data back in. But you can optimize your maintenance plans, your maintenance tasks, and then upload maintenance plans back into SAP. Okay, was there another question, Brent?
Thanks. Yeah, one other question is there a place within the software where you can model out kind of economic consequences, safety consequences, reputation costs, that type of stuff?
Sure. So the effects and the consequences, so they're called effects in RCM costs, and they're called, in ABSIM, they're called consequences. Those, I've been using them primarily to track the cost of a failure, but I'll just go back to RCM cost to show an effect. You'll notice there's also options for safety, operational, and environmental severities or impacts of a failure or an outage. So you can track those as well. Reputation is a new one that a lot of people are concerned about as well. While we don't directly have a category for that, some people might just reappropriate one of these. So it doesn't have to be operational, but to represent your reputation impact of a failure. So yeah, you'd use the effects or the consequences for tracking those.
Perfect, thanks.
Okay. There's one more optimization that we can do in RCM cost. And again, this can be done in both ABSIM and RCM cost. By the way, maintenance interval optimizations can also be done in ABSIM. I did it in RCM cost because it gives that nice plot. It gives the there we go. It gives this nice pretty graph, right? When you do it in RCM cost, ABSIM doesn't give the same pretty graph. It gives you the end result, but it doesn't give you the graph. So that's why I did RCM cost. So also that what can be done in RCM cost is the spare part optimization. So let's take a look at my pump spare. We'll go through the spare optimization for this pump. So what are we optimizing when we optimize a spare part? Well, all optimization includes a balancing act. With the maintenance interval optimization, what we're balancing is the cost of an unscheduled outage from not doing the maintenance versus the cost of the maintenance itself. We want to know how often do we need to do maintenance to minimize both those costs. For spare optimization, what we're optimizing is how many spare parts we need to keep on hand or do we need to keep available. What we're balancing is, again, the cost of unscheduled downtime or logistic delay time from not having a spare available versus the cost of keeping the spare on hand, which is generally comes from the storage cost of the spare part. If I open up the spare part properties for this pump, you can see we have 3 different levels of storage. We want to know how many spare parts should we keep on hand at each different level. So level 1 was generally on-site storage. So we can store spare parts on-site, and we'll have them immediately available, but that might be expensive. So here I put a $1 per hour per spare parts, per pump that we keep on hand. And again, I've just sort of picked that number up, but you might have to figure that out from the warehouse. I'm sure the warehouse has a square footage, and how much space are you devoting to storing these spare parts, and that's space that could be used for other things, right? So what's the cost of storing the spare part? The level 2 might be an off-site storage. It might be cheaper to store it off-site warehouse or a depot, but there might be increased logistic delay time. So in this case, we can store the spare part off-site for cheaper, but it takes longer to get it when we need it. And then lastly, is level 3 is the factory. If we don't have any at level 1 and level 2, we have to order more from the factory. And what's the logistic delay time for that? And here we have 168-hour or 1 week logistic delay time. If we don't have any pumps available, we have to wait 1 week before we can replace it. Okay, so let's optimize the spare part, figure out how many. And again, what we're going to do is we're going to consider minimum and maximums at each level. It's going to do a little bit of a brute force calculation. It's going to try every combination of level 1 and level 2 spare parts between the minimum and the maximum we specify, and report back which setting had the lowest cost, and also the unavailability of each setting. Sometimes people want to optimize spare parts by unavailability. How many spare parts do I have to keep on hand to make sure that I have minimal or no downtime, that I always guarantee to have one available? And so it'll also report that as well. So again, I'll tell it to try between 0 and 2 spare parts stored at level 1, and between 0 and 2, inclusive, of course, spare parts stored at level 2, and report back to me. So I'm going to select my spare part. Optimization is out of date, so I'm going to run the spare optimization. Okay, so here's what it recommends. So the x-axis is the spare storage configuration. So the numbers are given as a number dash and another number. They're level 1 storage dash level 2 storage. The bars themselves represent the cost associated with it. The color of the bar indicates whether that cost is due to unavailability or due to storage cost. And the red line represents the unavailability of that spare storage configuration. So you can see if we keep no spare parts on hand, every time we have a failure, we've got to order a new one from the factory. And that's very expensive because we have at least 1 week of downtime each time that happens. So we have a very high unavailability cost and a very high unavailability. If we keep 0 on hand at level 1 and 1 on hand at level 2, we have the downtime is significantly reduced. Rather than waiting 1 week, we only have to wait 1 day. And so our unavailability cost is reduced. Our storage cost, you can see there's a little sliver of storage cost. And our unavailability is significantly lower. So if we look through the bars, you'll see that the costs minimize right here. 1 spare part at level 1, 1 spare part at level 2 is where we have the lowest overall cost. We have basically no unavailability cost, and our cost is only coming from storage. Storing additional spare parts doesn't actually improve at all. We don't get lower costs by storing more. We actually just end up spending more on spare storage. So, and then also our unavailability, due to not having a spare part, is very, very low, on the order of magnitude of 10 to the negative fifth. So there's a very high chance we have a spare part available. We have very low downtime or unavailability from not having spares available. Okay, so if we would like the recommendation, again, if you like your recommendation, you can keep your recommendation. You can click the Accept Recommendations button. It will set, I'll go back and edit that pump. It sets the capacity at level 1 and level 2 both. And now I can rerun my simulations for RCM cost, or really this is aimed at the AVSIM model. I can jump over to the AVSIM, and since the thing is spares are directly shared between AVSIM and RCM cost, I don't have to do the data link to transfer the data. It's already updated on the AVSIM model because it's the same spare parts. So I can rerun my analysis, find out my new lifetime costs. Now, my overall costs now are on the order of magnitude 10 to the 6th. think they were, what, 10 to the 8th or 10 to the 7th before? I don't remember. I didn't write it down. But they were significantly higher than that on the first preliminary model that I ran. I can run the results. Again, I already did that. Get the new lifetime costs. Let's do this. I'll save the project as a save this as my RCM, my optimized RCM spares optimization, and I can compare it to the original by attaching a library. I'm gonna have to find it. Just let me search through here. Here's the previous one I had. I can go to my project comparison plot. Here was my original unoptimized maintenance, unoptimized spare storage, and here's, and of course I didn't think to name them. I'll name this one optimized. There we go. So this is my optimized model. This is the original model. So you can compare the costs between the two configurations. It breaks down spare storage, consequence, and purchasing costs of spares. So you can see how much I've saved. And again, this is something else that you might want to show management. This is what our current configurations cost, but if we optimize our maintenance, optimize our spare holdings, this is going to be our new cost. And so again, we can just quick print this, create a clipboard image, paste that into Microsoft Word. Here's my Word document, and I just hit paste, drop it right in, and print that out, or put it in another report. Okay. You can also print from the report designer. I don't know if I can get a report of a project comparison, but the report designer can also be used to, which one do I want to have some plots? Project comparison, I don't remember if a project comparison is one of my built-in plots, but there's a number of the different plots that I can use here. Okay, from that. I don't think I really have time to go much into the report designer. I know I said I would. I think we might have existing webinars that show some of the other features of the report designer. I hope I answered at least that question that I said I'd answer about printing out and showing management the results. I hope showing the plots showed at least some of that. Unfortunately, I don't have any time to go into more detail on the report designer or other features that you can get out. So maybe we can individually answer that question via email if I need to. If the person who asked it needs more information. Anyway, Brett, that's all I have. Unless there's any questions you want me to go through in our last minute or two before the end.
No, I believe those are the primary questions that kind of pertain to the group.
Sure.
I really appreciate it. I'm gonna switch back over to my screen here and just thank everyone for attending today. We do have a training coming up in Newport where it's a live training that you'd actually fly in, and Joe's conducting in December, and then we'll have pretty much quarterly trainings coming up in 2019 as well. If you have any questions, reach out. Let us, be a resource. Let us help you however we can. We really appreciate the partnerships we have with you guys, and let us know if any questions arise over the next, few days. We appreciate it and wish everyone a happy Tuesday. Thank you, guys.
Thank you.